문 좀 닫아주시겠어요? Okay, this is lecture 20 for circuit simulation. We have, including today's lecture, we have 6 remaining lectures. So before starting today's lecture, so first of all, let's review our previous lecture, lecture 19. So lecture 19 was the second lecture devoted to the interconnect. At the time, we have studied about copper wire. Previously, aluminum was the material used as an interconnecting material. However, now we introduce copper into it. So several years ago. And although copper is a difficult material in terms of reliability, if copper is included inside the silicon substrate, it is working as a contaminator. However, we have managed to adapt it in the mass production. So by using complicated procedure, anyway, we can keep our copper only in the metal wire, not diffuse over the silicon. So now wire capacitance. So previously we have considered in lecture 18 we have considered resistance, but wire capacitance is also important factor. So wire capacitance is given by just the distance and the relative permittivity inside the filling material. Therefore, we need low K material. Yes, so I have already introduced how can we make low K materials. And another one is at the end of our previous lecture, we have thought about long wire. For example, 1 millimeter long wire, and we have found that it significantly contributes to the delay. And even worse thing is, if our length is doubled, then the R can be doubled, and also capacitance then can be doubled. So it is the IC product is quadratically dependent on the length. So the bottom line is we must avoid the long line. So if we have a high capacitance, then of course in order to switch it on and off, we need more energy consumption. So the long wire line should be avoided. Then how can we avoid this long line? So I'm not talking about just 1 millimeter long, or also not 1 micrometer long or several hundred nanometer long line. So if this is quite long, then it is related with the part-to-part wire. So one part in a chip, this is really visible in microscope, and if we introduce such a long line, then that makes a critical impact on our performance. So we must do a clever floor planning to make our long wire as short as possible. Okay, so that was a brief review of our previous lecture, lecture 19. So now we will move to this chapter 8 devoted to the circuit simulation. So I assume that we will have two more lectures, including today's one for this chapter 8. And today we will talk about the general property of circuit simulation. And in the next lecture, lecture 21, we will talk about the specific MOS model, so BSIM or related concept. So let's go to the introductory part. Yes, this is the SPICE. Circuit simulation is actually sometimes called as just SPICE, although there are so many other programs, but it is just called as SPICE. And SPICE is the name originated from simulation program with integrated circuit emphasis. So they took just the first alphabet letters and make it as SPICE. I have read that the SPICE was originally developed as a term project in at the UC Berkeley. So at the time, a professor who was involved with some army came to the UC Berkeley. So he had a code for circuit simulation code. However, his code was under contract with the US Army. Not exactly army. I have no idea about which army, which force was involved. But anyway, that was a military contract. So he came to the UC Berkeley. After that, he gave Tom project to his student. So please make an open source version or license free version of my program. And several students actually tried, but only one guy actually succeeded, and it was SPICE. So of course, it is not the only effort for making the SPICE. However, initial development was done by the initial development was initiated as a term project. So it was 70s, and after that it became fully distributed over the universities and academia and companies, and you can just download it. However, that was a free version, the original SPICE version. After that, many companies just adopt this SPICE backbone code and add more capability and make it commercialized. So there are many commercial versions, and I think that most widely used one is ACE SPICE by Synopsys, but we have much more. This is quite expensive. And initially it was written in Fortran for punch card machines. So have you ever seen the punch card machine? So maybe you have seen it only in museum. And yes, so let me just skip this part. And the naming called as DEC and cards are all originated from our former days history, but we can just skip it. So I have prepared some slides to briefly introduce how can we do the circuit simulation inside the SPICE. But I think that we have already covered this one previously. So simply speaking, modified nodal analysis is performed in the SPICE. So modified nodal analysis simply means that if we have a certain circuit node, then we just apply the KCL over this node. Then that is the modified nodal analysis. Of course, here we have modified, instead of just a pure nodal analysis, we have modified nodal analysis, and it is related with resistance of inductor. So when we have inductor inside our system, then we also consider inductor voltage, not only in other branch current. So that is the modification. But I think that for our purpose, just nodal analysis is enough, so I will explain in that way. So let me just go through my slide. Consider a simple problem shown here. It is too simple. Here we have a voltage source and here we have a resistor. Then if I ask you, what is current flowing through this resistor? I'm not kidding. Actually, this can be easily answered by even pupils, but the answer is quite obvious to us, like VA over R1. Yes, everybody knows. However, the point is, how can we teach our computer to solve this problem? Although we can do it, but if you just buy certain PC, then your PC cannot solve it. So how can we teach our computer to solve this problem? Once we build a program which can solve this problem, then it is obvious that if we have quite complicated a network of resistors, instead of this simple one, let's say that we have a serially connected resistors. Yes, it is not that difficult even to us. However, how about this one? If we introduce parallel one and introduce another branch and another complication, if we go to in this way, although we understand the basic principle of circuit analysis, that would be quite tedious and difficult to us to get the really correct solution. However, fortunately, if we have a program to solve this simple system, then considering even a complicated network of resistors can be well done. And of course, if we have transistors inside it, that is not that much difficult for our program. That is difficult to us, although we understand the principle, but numerical calculation will be quite difficult. But once we know the program, we have the program, then it is quite easy task. So that's the reason why we want to build the program. So before starting the main discussion, we have to introduce some terminologies like elements. So we sometimes call circuit elements. So circuit elements means that some components like resistors, capacitors, of course, inductors, transistors, diodes, or many other electrical parts inside our integrated circuit. So simply speaking, a circuit is made by connecting the elements. So the word called as a circuit, there are some components called as elements, and their connectivity really determines the system. So it's like pretty close to this way. Here we have a society, and there are many different persons, one person, another person, and another person, and they are taking certain relationship. So that is a description for a small society, and quite similarly, a circuit can be seen as just a collection of elements. However, depending on their way of connection. Let's see. Then this circuit can be quite much different from the previous one. So we must understand there are two components. One is elements, the basic ingredients, and connection between them. Okay, so now in this slide we wanted to talk about element, and each element can have multiple terminals. Multiple means that more than one, 2, 3, 4, 5, something. For example, a resistor has two terminals. That is quite easy to understand. And how about diode? Diode has two terminals. Capacitor, yes, it has two terminals. And how about inductor? Yes, we also assume there are two terminals. Then are all circuit elements two terminal devices? Actually not. Another counter example is a MOSFET. If you have a MOSFET, then you have drain, gate, and source, and even you have body. So you have 3 or 4 terminals. If you have, for example, previous planar devices, certainly you have a body, and if you have, so nowadays more advanced devices, then you have just 3 terminals. But anyway, the number of circuit terminal or element terminal is not that fixed, and it depends on the type of your devices. So depending on the device, you can have different numbers of terminals. Okay. So this figure just shows the same circuit we are considering, voltage source and resistor. Then what is the circuit elements? Here, this red colored one, they are circuit elements, and they have two terminals here, and their connectivity is important. In the next slide, I will talk about this one. For example, if we make it this way, then that will be a certain thing. So now let's go to before talking about the connectivity, so there is a certain convention. You must understand this one. Terminal current. Terminal current is always decided to make incoming current as a positive one. So please think about this voltage source. Of course, if we wanted to analyze this circuit, then we will understand immediately, okay, the current will be VA over R1, but it means that this current flows this way, and flows this way, and this way, and this way. There will be a loop of current. That is loop current. However, usually we wanted to ask this question: what is terminal current? Not defined on this loop, but defined on each terminal of each element. So how can we determine this terminal current? So think about this one. Here we have a circuit element, and it can have multiple terminals: 1 terminal, 2 terminal, 3 terminal, n terminal, and for certain ICE terminal, let's just think about one special case, like current is now incoming. Then what is the sign of our ICE terminal current? In this case, we say that ICE terminal current is positive. But instead of that, happen to be, let's assume a case where current is escaping from the circuit element. Then we have to say the terminal current is negative. Then let's come back to our simple case. Since we have two circuit elements and each of them has two terminals, we can consider four different circuit terminals. So please try to get the sign of each component. For this terminal, we have positive quantity, and the same current flows. And for this lower terminal, actually current is now escaping from the resistor, so it has negative value. And yes, it has also positive value, and it has negative. So are you with me? So now we can have a different signs. So please note that we have a different signs. And let's just consider MOS, so MOSFET. So we have already thought about this concept previously. Source, gate, and drain. This is an MOSFET. And usually we have the current conduction through this way. Yes, we have it. Then, in many cases, at the steady state or low frequency case, we can neglect gate current. Then what happens? Then if we have positive drain current, then we have negative source current. If we neglect even the body substrate current, then they will have the same magnitude and the opposite sign. Okay, so that is the case. And let's go to our PMOSFET. So in the case of a PMOSFET, here we have a source, gate, and drain. Since source is highly biased than the drain, usual current conduction just follows in this way. Then what is the drain current of our PMOSFET? Our drain current in the case of a PMOSFET should be a negative number, and source current is a positive number. Please don't be confused with this sign convention. So always, the bottom line is quite simple. Always incoming current is regarded as a positive one. That is universal for this circuit simulation. So please understand this one. Now we are talking about node. So here we have one terminal and another terminal. Then they can be connected. Then this connection is made, and the meeting point between these two, it is called as a node. Now of course, here we have a terminal and here we have a line, but we assume that this line does not introduce any kind of electrical property. So they just shows the connectivity. And yes, so if, for example, now say once again, although we have a resistor and voltage source, but let's say that their distance, their physical distance is 1 millimeter. Then in this case, I think that this is not a good representation for our circuit. If we have just 1 millimeter long spacing between our source and load, in this case we have to introduce another circuit element to describe this 1 millimeter long wire. And what would be the best thing you can do? Maybe the distributed element description, just studied in our previous lectures, like 19 or 18, will be a good candidate. So please note that this kind of things does not contribute any property, just specifying the connectivity. Okay, so coming back to basic, node is a point to which multiple terminals are tied together. So usually we introduce that in order to enhance the visibility, but even without a dot, node is a node. And there is a special load called as ground, and when it is ground, then it is certain that voltage equal to 0. So it is ground. Then how can we describe a circuit? And now let's consider this a simple example once again. Now we have 1 volt electric motive force and 1 kilo ohm for this resistor. Then how can we describe this circuit? Of course, as a human being, we can just draw a circuit schematic. So draw this one, please solve this system. Then that is actually we have done up to now. However, how can we ask our program to recognize this circuit diagram? So I think that nowadays if we just take a picture and give it to ChatGPT, maybe it can recognize it as a RC or voltage and resistor, but please note that the initial invention of our SPICE program was done when it was 70s. So therefore, even graphical GUI, graphical user interface, was not available. So everything should be done in a text. So they have invented a file format called netlist. So here we have a netlist. So it is much easier to understand than directly start from this netlist. This is netlist. So it starts from its name. So please do not think about this one, just to concentrate. Okay, so program, just to find a new name. Oh, VA. Okay, maybe that is the name. And it starts from V. That is a voltage source. And I will call that VA. And it has two following entries, and first one is name of node, and second one is also name of node. So here 0, although 0 is a numeric number, however this is not just a numeric number, this is a new name of our ground. So simply speaking, it specifies it has two terminals, and its upper terminal is connected to out, and its lower terminal is connected to the ground. And let's go to the second line. Then it starts from R1. Since it starts from R, then we say that this is also a resistor, and it has two following node specification, and its upper node is connected to the out node, and it has just connected to the ground. And I just forgot the last quantity here and there. It has just numeric numbers 1 and 1000. What is the meaning of 1? In the first line, since it is a voltage source, what will be the meaning of 1? It is the magnitude of electromotive force is 1 volt. And what is 1000 in the case of a resistor? It means that the resistance is 1 kilo ohm. That's all for our netlist specification. Then maybe you feel something is missing. Each line just specifies the element, and there is no specification about node itself. For example, there exists a certain node called as out. It is connected to the upper node, upper terminal of a voltage source called as VA, and simultaneously it is connected to the upper terminal of a resistor R1. Such a kind of information is missing in this specification. It is really oriented to element. For each element, it just specifies its property, and additionally here, the terminal and node connectivity is provided. Then our program spies should collect them all. So after this is over, internally it says that it tries to collect node names. Which nodes are found? Yes, I have found a node, and I have found a node called as null, ground, and please try to find out terminals connected to this out. Okay, VA's upper node, upper terminal is connected, and R1's upper terminal is connected. In the case of ground, also it should perform such kind of consideration. So as a just a user, you don't have to explicitly consider this, how can I say, node consideration. You can just specify for each node what is the connectivity, local connectivity to the others. For example, maybe there can be another approach. I think that is more inefficient. For example, if we have a terminal and terminal without this node specification, maybe someone can try to make a certain grammar like the upper part of our voltage source is connected to upper part of our resistor. But it is really inefficient, because if we have multiple elements, then obviously it will fail, because this one is connected to this one, and simultaneously it is also connected to this terminal. So without introducing the intermediate concept called as a node, then the specification will be quite much difficult. So simply speaking, netlist really focused on your each element. Element-wise specification is the essential point of our netlist. Okay, so format for two-terminal devices is quite simple. Element label, its name, and node 1 and node 2, and value. What is the value? It really depends on the situation. So for example, if this is height home, then if there is a certain number, then what is the meaning of this number? Yes, maybe the height measured in centimeter scale, or weight of another guy, then what is the meaning? For example, 50. Then that will be the weight measured in the kilogram scale. So once again, in this specification, what is meaning of this value? That really depends on the type of your element, and who decide the type of element. So in this case, they made a really compact way to do that. So the first alphabet letter of its name determines the type. V, R. It means that this is a voltage source and this is a resistor. So it is not possible for us, for example, although this is a voltage source, I wanted to call it as R. It's not possible in this case, because every voltage source should start from V. So if you really wanted to certain R, then you have to say VR, something like that. Okay? So this is a really clever way and compact way. Then now let's go to one example. Here we have already more elements, 3 elements in it, and please try to build this netlist. Better way is already we have this solution. Then let's check whether we can easily build the system out of it. So C1, there is a capacitor called C1, and it is connected to in and out, and it has a number like 5 times 10 to the minus 12. What is it? This is picofarad. So we will have 5 picofarad capacitor. And another one is there is something called R1, and this one is connected to out and ground, and it has 2 times 10 to the 6. What is it? This is just 2 mega ohm. And finally we have V in, and it is also connected to in and ground, and it has the value of 1.5. What will be the meaning of this 1.5? It simply say that it is 1.5 volt battery. So that's it for the netlist format. After that, our computer program should connect them. Follow the node specification. Where is in? Here we have in and in, so we must connect them in this way. Where is out? Here we have out and out, then we must connect in this way. Where is ground? Here we have ground, and they are connected. So that will be the circuit schematic specified this netlist. Please compare this circuit schematic with the answer or the original question of our RC circuit. You can find that they are equivalent to each other. So now, even though you have quite much difficult complicated circuit, everything can be just described with netlist by a step-by-step manner. You just specify, concentrate on each element, and it will give you the full specification. Okay, then eventually we have to move to how can you solve this problem. Simply speaking, this is nothing but modified nodal analysis. And let's go to this one. Here we must identify the node, and here we have only one node called out. Of course, you may say that, oh, here we have also ground. However, in the case of ground, we don't care because ground is just fixed to the voltage 0. So we must concentrate on our out node. In the out node, we must apply the Kirchhoff's current law. It simply states that all of branch current, or the sum of all branch current, should vanish. This is a simple way. So here we have V I sub VA, I sub R1, A should be 0. And of course, that's true, but natural question is, what is I sub VA? And what is I sub R1? That should be answered. The nodal analysis simply means that don't care about it. Just consider the properties of your each element. That will give you the answer. So simply speaking, without bothered by this all kind of consideration, just to specify the property of voltage source and resistor. What is the characteristic equation for voltage source? Voltage source is characterized by the voltage difference between its upper node and lower node, or upper terminal and lower terminal, should be identical to the electromotive force. Here we have electromotive force of 1.0, and the difference between upper terminal and lower terminal voltage should be 0. That's it. And in the case of resistor, instead of voltage source, we must introduce Ohm's law. And Ohm's law says that our terminal current is simply given by this voltage source, or not voltage source, the difference between two terminal voltages, and it becomes just V divided by its resistance. We will have this form. Yes, so collecting them all, we can solve the problem. So how can you solve the problem? First of all, here we found that V out equal to 1.0, and from this information, from here we can understand we have a 1 milliamp for our V sub R1, and since we have here 1 plus 1 milliamp, then we can understand I sub VA will be minus 1 milliamp. That is the end of the story. Although it is quite simple, but anyway, we can do it even further expanded circuit. So you can do it. U means that here your program SPICE can do it. Okay. So now let's go through more details about SPICE. As I told you before, SPICE recognizes the type of your circuit elements with the leading the first alphabet letter. So for example, here you can say that V, any element starting from V is independent voltage source. R, that represents the resistor, and what else? You can find many other. For example, capacitor, inductor, you can find it. Also, you can have current source. And another one we can recognize is M. M is reserved for MOSFET. So if you have, for example, one transistor and another transistor, then you must have something like a M1 or M2 or whatever. Anyway, you have to start, you have some elements start from M. And diode, bipolar transistor, yes, there are many other components, but I think that MOSFET is the most important one you have to consider. And for example, also let's come back to my previous example. And well, here I have explicitly shown the numbers like this: 5 times 10 to the minus 12, or 2 times 10 to the 6, for example. However, it can be written as just 5 pico in this spice code, because it can recognize certain unit system, like if you say P, then it is just converted into 10 to the minus 12. Okay, so you can do it. Then now directly dive into an example of an IC circuit. Yes, please try to first build this system. Here we have a Vin. Okay, I will start from this Vin, and it is connected to in and ground. And here we have a R1, and this is Vin. It is connected to in and out. And finally we have a C1, and it is connected to out and ground. So let's connect them. Then, simply speaking, grounds are connected, and in are connected, and nodes are connected. Simply speaking, this is RC circuit connected to Vin. And if you go to this second line, R1 has 2K. It means that this is 2 kilo ohm resistor. And if you go to the last line, it says that 100 femto. Okay, this is 100 femtofarad capacitor. So this is much more visible than like 10 to the minus 13. Of course, they are the same. 10 to the minus 13 is corresponding to 100 femto. However, for engineers, they don't want to be bothered with these numbers. If you make any mistakes here, then what will happen? It has a huge number or quite a small number. So they wanted to have a more visible way or readable way. And another thing we have to consider is now this part. What is it? Now things are getting more complicated. For example, in this case, we just had a value 1.5. Then what is the meaning of this 1.5? It means that the voltage source or voltage difference between this upper terminal and lower terminal is always 1.5. So this is considered as just a DC source. However, we wanted to introduce a certain time varying signal. Then how can we specify a time varying signal? This is one way, or the piecewise linear voltage source. Of course, there is another specification, but this is one example. Here we have many seemingly quite complicated numbers, but their meaning is quite easy to understand. Because here we have 4 pairs of numbers, 2 numbers, and one number is assigned to time signal, and one number is a voltage value. So let me just draw in this way. This is time axis, and following its specification, at time equals 0, it has value of 0. Even at 100 picosecond, 100 picosecond, yes, it is 0. And 150 picosecond, yes, here we have 150 picosecond, and now it becomes 1 volt. After that, even after long time later, now here we have 1 nanosecond. So here we have 1 volt. What is the specification? Simply when we connecting them all, yes, we specify certain voltage waveform. So now we understand this piecewise linear specification just to describe a pulse which is rising in this time scale between 100 picosecond and 150 picosecond. The signal lies from 0 to 1 volt. Okay, we are ready to analyze this system, but without explicitly show the command line here. So analysis is not started. Here we have the line to start the analysis. That trend means that perform the transient simulation. And here we have T step and T stop. T step means that please simulate. This system is 20 picosecond spacing. So what is 20 picosecond in this case? Maybe here. That will be the time step for our circuit simulation. Of course, it always starts from 0, and here jump, 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 jump in this way. It is ends at 1 nanosecond. So after that, you can plug the output here. So if you have any question, then please let me know. And I wanted to say one comment. Yes, although this is the standard input file, however, it was tested for specific SPICE version. So what is this SPICE version? SPICE 3F5. This is the last version, last freely available version. I'm not quite sure you have already SPICE in your lab or in your laptop or anyway. If you don't have a SPICE, then I wanted to recommend you to install any version of SPICE into your environment. So I'm not saying that you must install this old version. So I just installed it because it is free. It is freely available. Also, there are so many other wonderful SPICE variants which can recognize this kind of netlist capability. So it's really up to you, but anyway, please have one. Okay. And my original intent to start this version thing is now, although we have a certain info file, this is tested for this version. If you have another version like HSpice, this is a different program. Although it is called as Spice, but it has much more extended capabilities. So it may have a slightly different specification or additional grammar. So please follow its own grammar. Otherwise, you cannot get the solution. Okay. Then now let's go to the MOSFET. as I told you before, MOSFET starts from M. And here, this is a simple example for grammar for our MOSFET, M. And you have the name, and here you have four different terminals, and four different terminals start from drain, gate, source, body. This is the given order, so you cannot swap it, so it is fixed by our convention. So please understand this start from drain, gate, source, body. It is applicable even to our PMOSFET. So then what will be the drain? So in this case, even in this PMOSFET, we have drain, gate, source, body. So and this is drain, gate, source, body. Okay, that is the specification shown here. And what is type? Oh, we have already studied this. M specifies that this is MOSFET type. However, here time means that more specific type of our transistor. For example, it can be NMOS or it can be PMOS sometimes, or it really depends on your specific technology. So, and otherwise, here you have width and length and area perimeter. Although here we have just a short line, but actually in our actual model we have several, really several parameters. So how many parameters? Please think about the order of number of parameters. So number of parameters nowadays is 1000 for a given MOSFET. So you can change it really almost everything. So then you can find so many different characteristics out of it. Okay, so of course all the technology do not have much, not so many parameters, but now the state of the art MOSFET models such as BSIM has more than 1000, over 1000 parameters. And now let's go to another example here. This is the example of DC analysis of our single MOSFET. So how can you understand this is a single MOSFET? Here we have M1. M1 has 4 terminals, and its drain is written as drain. Its gate is written as gate. Its source is now grounded, and also body is grounded, and it is N MOSFET. Yes. And WL, here we have 2.4 micrometer width and 1.2 micrometer length. Okay, this is the MOSFET. After that, even though we have a MOSFET here, we must also specify the voltage sources connected to the gate and drain. Where can you find it? Here you can find it. VGS. There is a voltage source called as VGS, and it is connected to the gate and ground. And you have another one called as VDS. It is also connected to the drain and ground. So when we connect them, then we can find quite obvious circuit where two independent voltage sources are connected to the gate and drain of our M1 MOSFET. After that, we wanted to perform the DC analysis. So here, please, it looks quite complicated. Okay, so please find this kind of a distinction. One, another. Okay, there is one specification and another specification. In the first specification, we have the voltage source to be swapped. So here we have drain voltage is start from 0 and it ends at 5 volt, and incremental value will be 0.05. So simply speaking, your VDS value will start from 0, 0.05, 0.1, 0.15, 0.2, 0.25, blah blah blah. In this case, you will have just sweeping the drain voltage up to 5 volt. Then you can find another swap here. What is it? Now VGS is starting from 0 and it will become 1.0, 2.0, 3.0, 4.0, and it will end at 5.0. So this second loop is outer loop, and this first loop is inner loop. So once we fix the outer loop VGS value 0, then sweep. After that, we increase voltage, gate voltage into 1.0, then sweep the drain. What is it? Simply speaking, what we do is like this: VDS and ID. That is calculated. Start from VGS, we just swap. We just sweep and another. This kind of analysis is performed with this kind of specification, outer and inner. Okay. Then let's go to the another example. This is an example involved with an inverter. So please try to draw the circuit schematic. Here we have M1. M1 is N MOSFET. Here we have M2. M2 is P MOSFET. Okay, I see. So here we have M1 MOSFET, and here we have M2 MOSFET, but that is P MOSFET, and its drain is connected to Y node, and their gate voltage is connected to A node. And in the case of the N MOSFET, its source is grounded, and in the case of a P MOSFET, its source is connected to VDD. What is VDD? Is it this reserved word for anything? So actually not. There is no reserved word like VDD. This is just ordinary node. Yes, after that they have the specification about the size. In the case of MOSFET, we have 2.4, 1.2. And in the case of P MOSFET, we have a 4.8, 1.2. Okay, simply speaking, they share the same gate length. However, P MOSFET's width is intentionally doubled compared with that of N MOSFET. That is quite common. And here we have voltage sources. One voltage source is called as VDD. Okay, then it is VDD, and its value is 5 volt, and it is connected to the VDD node and ground. There is another one, VIN, yes, and it is just kept at 0 volt. Why we have a 0 volt? Well, anyway, it is connected to the A node and ground. Then finally, let's try to connect them all. When connect A node, then you can find that here and there. The VIN is connected to M MOSFET and P MOSFET. Also, Y node, this output node, is connected. Their drain is shared, and also the source of our P MOSFET is connected to the VDD. Okay, that is just inverter. You know it. Then what we can do is the DC simulation. So in this case, already VDD is kept as 5. We can just increase V in voltage from 0 to 5 with 0.01 volt spacing. Then your Y value will be changed accordingly. After that, you can just print your input voltage and output voltage. Then that will give you a beautiful voltage transfer curve. But here I have one thing to mention. Although we say that okay, this is M MOSFET and this is P MOSFET, then the natural question is, well, you have an M MOSFET and P MOSFET, congratulations. Then what is the oxide thickness of this one? Do you have any idea? What is the threshold voltage of your M MOSFET? And what is the threshold voltage of your P MOSFET? Is there any information? Actually not. Or in the case of voltage source, it is perfectly self-contained. You don't have to any further specification for your ideal voltage sources. However, your MOSFET, just saying that WL, that is not sufficient. Even though you have W and L equal to 2.4, 1.2, if you make it with state-of-the-art device, then your performance will be much higher than the one built with older technology. So quite obviously, we need some specification about the technology. What is the MOSFET? That is specified in this case. Here, details are hidden here. All kinds of dirty things are there. So every detail is shown here. And although this is simply given in this way, in nowadays, this becomes more and more bigger and bigger, and this becomes more and more confidential nowadays. For example, if you are working with a certain foundry company, then to them, the performance of their transistor is really confidential, their IP. So they do not disclose it to everywhere. Only when you make the contract, when you pay the money to them and make a certain contract agreement about non-disclosure of this information. I'm not kidding. This is really serious business. Only when they do that, the users can access to this specification. Okay, so that is quite important thing. But that is usually hidden to designers. Designers sometimes just took the file and just install it and after that they do their design job, but actually everything is hidden in this type. Okay, so now let's go to our fifth homework. Oh, what happens? System seems to be stuck. Well, oh, okay. Here we have our fifth homework, and you have to submit our homework by uh, early in the morning and next Tuesday, maybe 21st day will be okay. Next Tuesday. We have only one problem. We have studied three different spice tutorial. However, just to do the first one, very simple one, RC circuit example. Please learn the simulation and report to your result. You will have quite a simple result because this is RC, but the reason why I ask you this question, this problem, is to get familiar with very early stage of spice. Okay, then if you don't have any spice, then please install it, and you don't have to reinstall your something. If you have any access to the spice more advanced version, then it is completely okay. So in my personal experience, spice 3.5 is fully available, and but you may try any spice. For example, if you have already installed HSpice in your lab, then just use it. You don't have to reinstall it into your server or your laptop. But if you don't have it, then please try to. But don't restrict yourself to only this older version, the authentic old version. But you can find many variants for this spice. So then please show the simulation result. Okay, this is the end of our today's lecture, and in the next lecture we will talk about the more detail about what is inside the technology file. So although there are so many different files, however, de facto standard of this model is so-called BC model. It is also came from Berkeley. Once again, you feel that maybe Berkeley contributed quite a lot to this field, and you may find this Berkeley BC model is the standard model. So I will prepare the lecture material for this BC model as a supplementary one for our circuit simulation part. So that will be lecture 21, and remaining 4 lectures I will try to go as much as far as possible. Okay, thank you for your attention. Bye.